This section explains why creation and annihilation operators are the natural language for identical particles. Particle labels are a fiction. Identical particles carry no fact of which is which, so the numbering used in Chapter 14 is pure redundancy, a description you then have to symmetrize back away by hand. The move of the chapter is to quotient that fiction out entirely. States become occupation numbers in Fock space, a count of how many particles occupy each individual state, nothing more. The symmetrization postulate, which is a constraint on states, migrates into a single algebraic relation on the operators that build those states. That relation is commutation for bosons and anti-commutation for fermions. The whole boson and fermion dichotomy collapses to one sign. That is the generative pattern. An unphysical label is killed by passing to the quotient, and the lost symmetry constraint is re-encoded in the operator algebra. This section explains how a one-body observable takes the same form no matter how many particles there are. A one-body observable asks every particle the same question and sums the answers. Total momentum, total angular momentum, the sum over all particles I of f of I. Its physical content cannot depend on which particle you are looking at. So a sum over n indistinguishable copies must collapse to something blind to n. It does. The observable becomes the sum over k and l of the single particle matrix element, FKL, times the creation operator A, dagger, sub K, times the annihilation operator A, sub L. The particle count vanishes from the expression outright. One operator serves every value of n. Each term reads as a transfer. Annihilate a quantum in the state U a sub L, recreate it in the state U a sub K, weighted by the single particle matrix element FKL. This is the first dividend of second quantization. Symmetrization stops being a step inside the calculation and becomes the grammar of the creation and annihilation operators themselves. This section explains the single move that defines the field operator. Take the annihilation operator and let its label run continuous. In Chapter 15, you built annihilation operators indexed by a discrete state, I. Here, you swap that basis for the position eigenbasis, and the operator a sub I, our operator, to an operator-valued field. Valued a value of R, one annihilation operator per point of space. The definition says psi of R equals the sum over I of U sub I of R times a sub I. This reads exactly like expanding a wave function on basis functions, except the coefficients a sub I are operators, not numbers. The classical field, nothing new is postulated. Same Fock space, same commutators and anti-commutators, merely a continuous index. The chapter exists for this single rewriting, which then lets every symmetric observable and later the electromagnetic field in chapters 19 and 20 be quantized the same way. This section explains the two-body operator, the smallest object in physics where particles act on each other. Interaction is the first physics that needs two particles at once. A one-body operator relocates a single particle, kinetic energy, and external field. The two-body operator is the smallest object where particles feel each other, and every pairwise interaction, Coulomb, a collision, lives exactly here, nowhere lower. You build it by summing a binary operator over distinct ordered pairs. Exclude the case where Q equals Q prime, which secretly collapses to a one-body term. Then halve to avoid double counting the same pair. In Fock space, it crystallizes into one template, annihilate 2, create 2. Written out, that is a I dagger, a J, dagger, a L, a K, 2 creation operators against 2 annihilation operators. The creators balance the annihilators, so total particle number is conserved for free. The pattern generates its own ladder. An n-body operator is n creations against n annihilations, no more. This section explains how to build a better trial state for identical particles by pairing them. Build the trial state from pair creation operators acting on the vacuum rather than single particle ones, and the variational family widens by exactly the degree that matters. A Fock state carries only the statistical correlations forced by indistinguishability, letting the pair wave function, chi of R1 minus R2, vary threads in the dynamical correlations that interactions demand. The leverage here is precise. A standard Hamiltonian couples particles pairwise, so binary correlations alone fix the potential energy. 3-body and higher terms exist, but they never enter it directly. Optimize the pair correlation, and you have already captured what the energy sees. Hartree. Fock falls out as the special case where the pair degenerates to a product. Treating each bound pair as a molecule is the generalization. This section explains why the order of interaction in a Hamiltonian decides which correlation the energy can actually see. Interaction order dictates which correlation the energy can see. A standard Hamiltonian couples particles 2 at a time, so the mean energy is a functional of the pair correlation alone, the 2-body distribution, and nothing above it. 3-body correlations are genuinely present in the state, and they act physically, but the energy is blind to them. They never enter its expression directly. That single fact is why this chapter's paired states, which tune only the binary correlation key of R1 minus R2, already reach very good n-body accuracy. You optimize exactly the object the energy depends on. Promote the Hamiltonian to 3-body forces, and the argument shifts. The 3-body correlation becomes the term that carries the energy, and pairing alone would no longer suffice. This section explains why quantizing the electromagnetic field demands almost nothing new. The home move is a change of variables, nothing more, but chosen so that quantization becomes automatic. Fourier transform Maxwell into reciprocal space, and the field splits in two. The longitudinal part collapses to Coulomb's electrostatic field, a mere function of particle positions with no life of its own. The transverse part is the radiation. Each transverse mode evolves as e to the minus I omega t, with omega equal to c times k. That is the equation of a one-dimensional harmonic oscillator. Its normal variable is the classical shadow of the annihilation operator, waiting in Chapter 19. The whole chapter is this single recognition. The electromagnetic field is a stack of independent oscillators, so quantizing it costs nothing you do not already own. This section explains how the electromagnetic field is reduced to oscillators before quantum mechanics ever enters. Diagonalize a linear field and it stops being a field. It becomes a countable bag of independent oscillators, one per normal mode. That is the move Chapter 18 prepares. Fourier transform Maxwell in vacuum, and the transverse field factors into modes, each evolving as e to the minus I omega t, with omega equal to c times k, one harmonic equal to c times k, one harmega equal to c times k, one harmonic oscillator apiece. The longitudinal part is no genuine degree of freedom. It is just Coulomb, slave to the charges, eliminable by gauge. So radiation reduces to decoupled oscillators before any quantum is invoked. Quantization then costs nothing new, promote each mode's normal variable to the oscillator's annihilation operator, and the excitations are photons. The chapter is the classical hinge. Cette section explique pourquoi le rayonnement électromagnétique doit être quantifié. L'atome excité seul devrait rester excité pour toujours. La mécanique atomique est stationnaire, rien ne le fait tomber. Il tombe pourtant en émettant un photon. L'émission spontanée est le fait expérimental qui force la main. Le champ mépo plus rester classique, tandis que la matière est quantique. Le semi-classique n'a plus de couplage à offrir qu'on le champ, incident est nul. Le chapitre existait pour combler ce vide, littéralement le vide de photons, qui fluctue toujours. Le juste est le suivant. Chaque mot propre du champ est un oscillateur harmonique. Donc quantifier le rayonnement, c'est le même passage où aux opérateurs à être à daguer. Par mot, les photons sont les quanta. This section explains why the electromagnetic field must be quantized. An excited atom in the dark decays anyway, and semi-classical theory forbids exactly this. Zero classical field means zero interaction, so the excited state should sit stationary forever. Spontaneous emission is the forcing anomaly. The field must carry its own degrees of freedom. The vacuum is not empty. The whole chapter turns on one substitution. Decompose the free field into normal modes. Each mode obeys precisely the algebra of a harmonic oscillator. So you quantize the field by quantizing that ensemble, replacing each normal variable alpha with an annihilation operator, a hat. The photon is one quantum of one mode's excitation. Everything downstream is bookkeeping, and the check is that Heisenberg's equations reproduce the Maxwell-Lorentz equations. This section explains how one interaction vertex generates the whole zoo of ways an atom trades photons with light. The interaction, Hamiltonian, is linear in the field operators. So the transverse electric field goes as the annihilation operator, plus the creation operator, plus the creation operator, a dagger. That splits every atom and light matrix element into exactly two elementary acts. Annihilate a photon, which is absorption, or create one, which is emission. Every richer process is these two composed. Scattering is absorb, then emit. Photoionization is absorb into the continuum. Each matrix element factors into three independent pieces, one per symmetry. The translation operator, the exponential of plus or minus I times k sub I dotted into R, enforces momentum. The odd vectorial dipole operator, d, enforces parity and angular momentum. Energy binds the rest. Here is the asymmetry that carries everything. Absorption scales as n sub I, the occupation of the incident mode, while emission scales as n sub I plus 1. That surplus 1 survives into empty space. It is emission spontanée, spontaneous emission already latent in the vacuum. This section explains why every optical process in the chapter is one object seen at different orders. Every process the chapter names absorption, induced and spontaneous emission, elastic and Raman scattering is a single amplitude. It is the matrix element of the evolution operator U taken between the initial state phi I and the final state phi I and the final state phi F. Expand U in powers of the dipole interaction and the whole zoo falls out by vertex counting, stretches of free evolution separated by interaction points, one vertex per photon exchanged. One annihilation vertex is absorption. One creation vertex is emission. Two vertices are scattering. Nothing is added but the counting. Nothing is added but the counting. The catalog of processes is really the perturbation series of one operator read off order by order. Only quasi-resonant scattering breaks the count, forcing the series to be resumed non-perturbativement. This section introduces entanglement as the closing chapter of Tome III, and its point is to extract the consequences of a single inversion. Maximal knowledge of a whole no longer implies maximal knowledge of its parts. That inversion of the classical part-whole relation is entanglement itself, and this final chapter exists to draw out what follows from it. A total state that refuses to factor as the tensor product of a state phi A with a state chi B leaves each subsystem describable only by a reduced density matrix. That reduced matrix is a genuine statistical mixture, meaning the trace of rho A squared is less than 1, even though the pair as a whole is a pure state. Schrödinger's line, written in 1935, carries the weight of the idea, la meilleure connaissance, possible du tout non plus, passe nécessairement la meilleure connaissance possible de ses parties. Bell's inequalities then turn this metaphysical strangeness into a number. Local realism cannot exceed that number, and quantum correlations do. The claim is falsifiable, not philosophical. This section explains entanglement as the one structural fact beneath the whole chapter. Entanglement is the single fact that a composite state can fail to factor. No product state, some state of A, tensored with some state of B, reproduces the joint state, psi. The whole chapter is that one non-factorization, read from different angles. The whole outstrips its parts. Specifying A plus B perfectly as a pure state does not fix A, whose reduced description collapses to a statistical mixture. Cohen, Tanuji ends. Tome 3 here because this inverts the classical parts and whole law, where the total is exactly the union of its parts. Schrödinger called it the characteristic trait of quantum mechanics, the single defining one rather than one trait among many. Measurement, decoherence, and pointer states, which path, complementarity, Bell, non-locality, each is this one break, specialized. That gives you the way to predict the next. Any quantum surprise is correlation resident in the whole, absent from every part.